everyone. I am Dr. Manisha Verma, teaching physics in Acharya Narendra Dev College, University of Delhi. Recently, I have started with a lecture series on thermal physics, as you may be aware. In the last few lectures, I had started with a discussion on thermodynamic potentials. I have discussed what are thermodynamic potentials, what is the significance of thermodynamic potentials, which thermodynamic potential can be used under what conditions, and then I moved on to discuss the applications of thermodynamic potentials. In the applications, we derived the TDS equations, we derived the energy equations, we derived the Clausius-Clapeyron equations, besides other applications. So in continuation of my earlier lecture, today let me again concentrate on thermodynamic potentials. This is the fifth lecture in my series on thermodynamic potentials. Today we will discuss the sixth application of the Maxwell's relations, which have been derived on the basis of thermodynamic potentials. Let us discuss how Maxwell's relation help us in interpreting what would be the change in temperature during an adiabatic process. Adiabatic process, I repeat, is a process in which the entropy is a constant. Let us consider the adiabatic expansion of a gas. In adiabatic expansion, the entropy S of the system remains a constant. From the Maxwell's relation, we have delta T by delta V at constant entropy is equal to minus delta P by delta S at constant V. You will appreciate the negative sign here. This is because S, P, T and V are occurring in anti-clockwise direction. Now, by definition of entropy, we have delta Q is equal to T delta S. Thus, we can write 1 by T delta T by delta Vs is equal to minus 1 by T delta P by delta S V. Here we have divided the earlier equation by T, a simple step, which will now give us minus delta P by delta Q because T delta S is equal to delta Q. So, I can replace T delta S by delta Q. Right hand side we have the volume constant and the left hand side we have the entropy constant. Thus, we can write delta T by delta V at constant S is equal to minus T delta P by delta Q at constant V, which will give me minus T delta P by delta T at constant V, delta T by delta Q at constant V. So, rearranging the terms, I get minus Tp into 1 by P. Here I have multiplied and divided by P, delta P by delta T at constant V into delta T by delta Q at constant V. You will appreciate why I have multiplied and divided by P by the following explanation. 1 by P delta P by delta TV is called the coefficient of pressure expansion or the increase at constant volume. Thus, we can write the above as minus Tp kappa 1 by Cv, where Cv is delta Q by delta T at constant V. As gases expand on heating is positive, Cv and all quantities are positive, thus delta T is negative or cooling is produced during adiabatic expansion. So, what have we seen? we have seen that using Maxwell's relation, we can show that cooling is produced during adiabatic expansion. Now let us consider the opposite process, that is a process in which the compression of a gas is taking place under adiabatic conditions. In adiabatic compression, the entropy S of the system remains a constant and the pressure is increased. Because we have to compress the gas, therefore we have to increase the pressure. We are interested in finding delta T by delta P at constant S. Why constant S? Because we are finding for adiabatic conditions. From Maxwell's relation, we have delta T by delta P at constant S is equal to delta V by delta S at constant P. Here we have a positive sign because S, P, T, V are occurring in a clockwise direction. Now, as done before, we divide by temperature and we get 1 by T delta T by delta P at constant S is equal to 1 by T delta V by delta S at constant P. By definition, T delta S is delta Q. So, the right hand side gives me delta V by delta Q at constant P. So, what do we get? We get delta T by delta P at constant S is equal to T times delta V by delta Q at constant P, which is equal to T delta V by delta T at constant P into delta T by delta Q at constant P. Now, what do? We multiply and divide by V. So, we get V into T 1 by V delta V by delta T at constant P into delta T by delta Q at constant P. Alpha is defined as the coefficient of volume expansion at constant pressure. So, what do we get? We get Vt alpha into 1 by Cp, where Cp is delta Q by delta T at constant pressure. Now, because Tv alpha by Cp is a positive quantity, dP is also positive, which means that adiabatic increase in pressure produces heating effect, because now dt is greater than 0, which means T2 minus T1 is greater than 0, or T2 is greater than T1, which means heating has taken place. So, effectively, in the discussion of this application, we have seen that using Maxwell's relation, we are able to show that adiabatic compression produces heating and adiabatic expansion produces cooling. If you remember, in one of my lectures, I had discussed the Joule-Thomson effect. Therein also we had shown the same thing. Now let me discuss some very important problems pertaining to the applications of Maxwell's relations. The first problem: show that the ratio of adiabatic elasticity to the isothermal elasticity is equal to the ratio of the two specific heats. This means that we have to show that if E represents the elasticity, then Es by Et is equal to Cp by Cv is equal to gamma. By definition, isothermal elasticity can be written as E subscript T is equal to minus V delta P by delta V at constant T. Always remember, elasticity is the reciprocal of compressibility. Similarly, we can write adiabatic elasticity as Es is equal to minus V delta P by delta V at constant S. Let me take the ratio of Es and Et. On taking the ratio of Es and Et, we get Es by Et is equal to delta P by delta V at constant S by delta P by delta V at constant T. Now let me write the equation in a special form. Why do I do this? Because essentially I have to show that Es by Et is equal to Cp by Cv. So I have to manipulate the right hand side in such a way that using Maxwell's relation I am able to get the desired relation. The numerator shown on the previous slide can be written as delta P by delta T at constant S into delta T by delta V at constant S. So I have divided or just split the term into two terms. The denominator similarly can be written as delta P by delta S at constant T into delta S by delta V at constant T. Now what do? We manipulate the right hand side still further. We write the right hand side as delta S by delta P at constant T into delta T by delta V at constant S divided by delta T by delta P at constant S into delta S by delta V at constant T. So what have we done in this step? We have taken the denominator first term delta P by delta S at constant temperature into the numerator, and we have taken one term of the numerator into the denominator. From Maxwell's relation, we have delta S by delta P at constant temperature is equal to minus delta V by delta T at constant pressure, and delta T by delta V S is equal to delta P by delta S at constant volume. Delta T by delta P at constant S is equal to delta V by delta S at constant pressure, and delta S by delta V T is equal to delta P by delta T V. So you can see that we are using all the four Maxwell's relation in this particular problem. If we substitute these equations in the previous equation, we get Es by Et is equal to minus delta V by delta Tp divided by delta V by delta S at constant pressure into minus of delta P by delta S at constant volume divided by delta P by delta T at constant volume. So just interpreting these further, we get delta S by delta T at constant pressure divided by delta into delta T by delta S at constant volume, which is equal to T times delta S by delta T P divided by T delta S by delta T V. Here we have multiplied and divided by T because we are interested in finding Es by Et into the desired form. The numerator is delta Q by delta T at constant pressure, and the denominator is delta Q by delta T at constant volume. Why? Because delta Q is T delta S. So the numerator is Cp and the denominator is Cv, which we know is gamma. So hence proved, we have shown that the ratio of the adiabatic elasticity to the isothermal elasticity is the ratio of the specific heats, which can also be written as gamma. Now let me move on to the second problem. This is again a very interesting problem. Cp minus Cv is equal to T E V alpha square. T is the temperature, E is the elasticity, V is the volume, alpha is the coefficient of volume expansion. While discussing the applications of Maxwell's relation, we have seen in the previous lecture that Cp minus Cv is equal to T times delta P by delta T at constant volume into delta V by delta T at constant pressure. To get the desired relation, let me take pressure as a function of two independent variables, volume and temperature. That is, P is equal to P volume comma temperature. This would mean that dP is equal to delta P by delta V at constant T into dV plus delta P by delta T at constant volume into dt. Now, if the changes are taking place at constant pressure, we have dP is equal to 0. Thus, the left hand side of the previous equation becomes 0. So, what do we get? We get 0 is equal to delta P by delta V at constant temperature into dV plus delta P by delta T at constant volume into dt, or delta P by delta T at constant volume dt is equal to minus of delta P by delta V at constant temperature dV. Rearranging these terms, we get delta P by delta T at constant volume is equal to minus delta P by delta V at constant temperature into delta V by delta T at constant pressure. Why we have taken constant pressure? Because we are considering the changes are taking place at constant pressure. Now substituting 8th in 7th, we get Cp minus Cv is equal to minus T delta V by delta T at constant P square into delta P by delta V at constant temperature. By definition, E is equal to minus V delta P by delta V at constant temperature and is defined as isothermal elasticity. Alpha is defined as 1 by V delta V by delta T at constant pressure. So we get Cp minus Cv is equal to T E square V alpha. Now let us discuss the third problem. Prove that the ratio of adiabatic to isobaric coefficient of volume expansion is 1 over 1 minus gamma. That is, we have to show that alpha S by alpha P is equal to 1 over 1 minus gamma, where gamma is Cp by Cv. So, by definition, the coefficient of volume expansion under adiabatic condition is defined as alpha S is equal to 1 by V delta V by delta T at constant S, and under isobaric condition alpha P can be written as 1 by V delta V by delta T at constant pressure. Therefore, the ratio alpha S by alpha P can be written as delta V by delta T at constant S by delta V by delta T at constant pressure. Taking the numerator to the denominator. So, what do we get? 1 by delta T by delta Vs into delta V by delta T at constant pressure. From Maxwell's relation, we have delta T by delta V at constant S is equal to minus of delta P by delta S at constant V. Substituting, we get alpha S by alpha P is equal to minus 1 by delta P by delta S at constant volume into delta V by delta T at constant pressure. This would give me minus 1 divided by delta P by delta T at constant volume into delta T by delta S at constant volume into delta V by delta T at constant pressure. Here we have split delta P by delta S at constant volume term into two terms. Now what do we do? The term occurring in the denominator, delta T by delta S at constant volume, is taken to the numerator. So we get minus delta S by delta T at constant V divided by delta P by delta T at constant volume into delta V by delta T at constant pressure. Multiplying the numerator as well as the denominator by T, we get minus T delta S by delta T at constant volume divided by T times delta P by delta T at constant volume into delta V by delta T at constant pressure. But T delta S by delta TV is equal to CV. Why? Because T delta S is equal to delta Q, and delta Q by delta T at constant volume is defined as specific heat at constant volume and is represented by the symbol CV. Further, in my last lecture, we had seen that T times delta P by delta T at constant volume into delta V by delta T at constant pressure is equal to Cp minus Cv. Here, Cp, Cv are the molar specific heats of a gas at constant pressure and at constant volume respectively. Thus, we have alpha S by alpha P is equal to minus Cv by Cp minus Cv. So, rearranging the terms, we get Cv by Cv minus Cp. Dividing the numerator as well as the denominator by Cv, we get 1 over 1 minus Cp by Cv. What is Cp by Cv? That is gamma. So, we get 1 over 1 minus gamma. Hence, proved. The problem is solved. Now, let us discuss one more problem. Show that the ratio of adiabatic to isochoric pressure coefficient of expansion of a gas is gamma by gamma minus 1. The pressure coefficient of expansion of a gas is defined as the ratio of change in pressure per unit pressure change in temperature, that is 1 by P delta P by delta T at constant S when we are considering adiabatic, and when we are considering isochoric we have the subscript V. So, we can thus write the term as 1 by delta T by delta P at constant S into delta P by delta T at constant V. Using Maxwell relation and substituting, we get 1 by delta V by delta T at constant pressure into delta T by delta S at constant pressure, delta P by delta T at constant volume. Rearranging the terms, we get the desired relation, that gamma is equal to gamma by gamma minus 1. I hope these problems were useful to you in understanding the concepts, how to apply Maxwell relation, and how can we solve problems using Maxwell relation. Thank you.